I am Anjan Kumar Bhuiya from Vishwabharati Shantiniketan. Already we have discussed 4 chapters in group theory. Today we will start ring theory. The first chapter in ring theory is polynomial rings. The polynomials dates back to 1650 BC. Egyptians used polynomials to solve linear equations. In 1600 BC, Hindus developed a method to solve quadratic equations, but the polynomials as we know today, or the notions, symbols which we use presently to represent a polynomial was unknown till 1700 AD. Today specially we will give emphasis on the algebraic structure of the set of all polynomials. We will see that the set of all polynomials over a commutative ring with unity is a commutative ring with unity, and my second emphasis is on the formalization of the symbol x, which is known to us as an unknown quantity, which I think a pseudo definition which can't be treated as a proper definition. So, let us start our content. In this chapter we have 4 objectives. The first objective is to give a formal definition of polynomials. Our second objective is to show that the set of all polynomials over a commutative ring with unity is also a commutative ring with unity. Our third objective is to define formally the degree of a non-zero polynomial. Our fourth objective is important one. This is to identify units in the polynomial ring. Since the polynomial ring is never a field, so it is very important to note why it is not a field. It is not a field because there are so many polynomials. Actually, the most of the polynomials are not units. Only few special are units in the polynomial rings. Before coming to the formal definition of polynomials, let us review what we know by a polynomial. Polynomials to us are the expressions of the form 6 plus 7x plus 3x square minus 5x cube plus 2x square. Here the coefficients 6, 7, 3, minus 5, 2 are integers which can also be treated as real numbers also, and the degree of this polynomial we know that it is 4. A polynomial may have any arbitrary degree, and some of the polynomials are defined as follows. Say for example, we have 2 polynomials a0 plus a1x plus a2x square and b0 plus b1x plus b2x square plus b3x cube. Sum of 2 polynomials is done actually by summing the respective coefficients, that is we add a0 and b0 to get the constant term, and to get the coefficient of x we add the coefficient a1 of the first polynomial and the coefficient b1 of the second polynomial and so on. And to define product of 2 polynomials we take only the coefficients into considerations. Thus, in the study of polynomials, presence of x is symbolic and the coefficient plays the most important role. This observation leads us to define polynomial as an infinite sequence a0, a1, a2 and so on, where each ai is an element of R and R is a commutative ring with unity. Reason behind considering R as a commutative ring with unity to perform addition and multiplication of polynomials. That is why we need two operations, namely addition and multiplication on R. And this is the reason we consider R to be a commutative ring with unity. Since a polynomial contains only finitely many terms, strictly speaking finitely many non-zero terms, that is why we consider only those infinite sequences which has all but finitely many ai are 0. The set of all polynomials over a commutative ring with unity R is denoted by this symbol, which is read as R x, and this is the set of all infinite sequences where the terms of the sequence is in R and almost all, that is all but finitely many ai are 0. And naturally, definition of addition should be set as a0 plus a1 plus a2 and so on, plus the second polynomial b0 plus b1 b2 and so on equal to a0 plus b0 a1 plus b1 and so on. That is, the addition is component wise, and the multiplication should be defined as this, where each Ci is obtained as a sum of the products of ai and bi. Thus, C0 becomes a0 into b0, whereas C1 becomes a0 into b1 plus a1 into b0 and so on. It is easy to check that the set Rx of all polynomials is a commutative ring with identity 1, where the 0 element is 0 0 0, that is the infinite sequence whose all terms are 0 of the commutative ring R. And here the identity 1 is actually this infinite sequence, where the first term is 1 and all other terms are 0. And the negation of a polynomial a0, a1 and so on is the polynomial whose terms are minus a0, minus a1 and so on. The ring R can be embedded in the newly constructed ring Rx of all polynomials over R. For this, let us define a mapping from R to Rx by A goes to the polynomial whose first term is A and all other terms are 0. This is a homomorphism of rings, and at the same time this is 1 to 1, and thus every commutative ring R with unity can be considered as a subring of the ring Rx of all polynomials over R. Since this mapping is a homomorphism, so it is justified not to distinguish between A and the polynomials whose first term is A and all other terms are 0. If we agree to consider this polynomial as the element A of R, then we get the expression of polynomials into the classical form. Now, let me define the symbol x formally. The particular element 0, 1, 0, 0, 0 and so on is called the indeterminate over R and is usually denoted by x. Then according to the definitions of addition and multiplication of polynomials over R, we have x square equal to 0, 0, 1 and so on. X cube becomes the polynomial whose first 3 terms are 0, the fourth term is 1 and all the rest terms are 0. And similarly, we have x to the power 4, x to the power 5 and so on. And then if we assume a1 to be the polynomial whose first term is a1 and all other terms are 0, then the product of a1 and x becomes the polynomial whose first term is 0 and only the second term is a1 and all other terms are 0. Similarly, a2x square becomes the polynomial whose third term is a2 and all other terms are 0. And thus we have the polynomial a0, a1, a2, an and all other terms are 0 is equal to the expression a0 plus a1x plus a2x square plus so on plus an x to the power n. This is our classical form of polynomials. Thus, we see that the addition and multiplication on the ring of all polynomials is defined in such a way that it is compatible with our classical expression of polynomials. But we define polynomials as an infinite sequence just to get an arbitrarily many terms in a polynomial and to define the indeterminate x in the framework of abstract algebra. For example, consider the polynomial ring Z6x, that is the set of all polynomials over the ring Z6, and consider two polynomials f(x) equal to 2x cube and g(x) equal to 3x cube. Thus, we see that product of these two polynomials becomes 0 in the ring Z6x. This shows that the polynomial ring Z6x is not an integral domain. Thus, though every polynomial ring is commutative and contains unity, it may not be an integral domain. In abstract algebra, always when we have some non-empty sets, then we try to define some operations on this set so that the set constructs or constitutes some algebra of standard type. Say either it becomes a group or a ring or a field or a vector space. Here our advantage is that to define polynomial, we have already defined addition and multiplication of polynomials, and we have seen that the set of all polynomials forms a commutative ring with unity. Now, we have seen that this is not an integral domain, may not be an integral domain. Sometimes it may be an integral domain also, which we will see in the next result, where we will characterize those commutative rings with unity R for which the polynomial ring R x becomes an integral domain. Now, we characterize the commutative rings R for which the polynomial ring R x becomes an integral domain. We see that R x becomes an integral domain if and only if the ground ring R is also an integral domain. To prove the result, first assume that the given ring R is an integral domain. Then, as we have seen earlier, R x is a commutative ring with unity. Consider two elements f x and g x from R, and these two are two non-zero polynomials. Since these two polynomials are non-zero, so we may assume without loss of any generality that both a n and b m are non-zero. Now, a n and b m are two elements of R, and since R is an integral domain, so it follows that a n into b m is non-zero, and since a n into b m is non-zero, so the product f x into g x becomes non-zero, since the coefficient of the term last term C n plus m is non-zero. This implies that the product of these two polynomials f x into g x is non-zero when f x and g x are considered to be non-zero polynomials, and hence in R x there is no zero divisors. Thus, it follows that R x is an integral domain. The converse follows directly, since R can be treated as a subring with identity of the polynomial rings R x. Now, we define degree of a non-zero polynomial. Suppose p x be a polynomial whose all terms after a n x to the power n are 0. Then the degree of p x is defined to be n if a n is non-zero, and in this case a n is said to be the leading coefficient of p x. The speciality of n to be the degree of this polynomial p x is that n is the largest positive integer such that a n is non-zero. Since in case of zero polynomial we have no non-zero coefficient a I, we do not define degree of the zero polynomial. For example of degree of polynomials, we have degree of this polynomial is 3. Note that the largest positive integer n such that a n is non-zero is 3, and here the leading coefficient is 5. Thus, the degree of this polynomial becomes 3, and similarly degree of this polynomial is 0, since the non-zero term, here is the only one which is 2 and which is nothing but a 0. So, 0 becomes the degree of this polynomial 2. And now, we consider degree of the sum of two polynomials. Is there any relation between degree of f x plus g x and degree f x degree g x? Let us see. Consider f x equal to 1 plus x and g x equal to 1 minus x. Then both f x and g x are polynomials of degree 1, whereas their sum f x plus g x is a polynomial of degree 0. We will see that degree of f x plus g x can never exceed degree f x and degree g x. At most, it can attain the maximum of degree f x and degree g x. Before going to the detail of the proof, let us see product of two polynomials. In case of product also, degree f x and g x is always less than equal to degree f x plus degree g x. Actually, this follows from the fact that for any x, x to the power m into x to the power n equal to x to the power m plus n. From this fundamental law of indices, it follows that degree of f x into g x can never exceed degree f x plus degree g x. Formally, these two observations can be stated as follows. Let R be a commutative ring with 1 and f x g x be two non-zero polynomials in R x. If f x into g x is a non-zero polynomial, then degree of f x into g x is less than equal to degree f x plus degree g x, and the equality holds if R has no divisor of 0, and if their sum is a non-zero polynomial, then the degree of the sum is less than equal to max of degree f x and degree g x. We omit the proof of this result here, which can be found in the E content. Consider a non-zero polynomial f x over R. If it is a unit, then we have another polynomial g x in R x such that their product becomes 1. If R is an integral domain or a field, then we know that degree of f x into g x is equal to degree of f x plus degree of g x, and hence it shows that no constant polynomial can be a unit. Thus, for f x equal to a 0 plus a 1 x plus so on plus a n x to the power n to be a unit, we must have a 1, a 2, a n are 0 divisors. In the next slide, we show that even this is not sufficient. Already we have seen that if R is an integral domain, then the polynomial ring R x is also an integral domain, but R x is never a field even if R is also a field. The reason is very simple. If we consider the polynomial x, then it has no multiplicative inverse. Now, let us see which of the polynomial in R x qualify to have a multiplicative inverse. This is the result which characterizes all polynomials which are unit. let R be a commutative ring with 1. Suppose f(x) be a non-zero polynomial, then f(x) is a unit if and only if the constant term a0 is a unit and all other ai are nilpotent in R. Here I will not go into the detail of the proof. Let me sketch. First, assume that a0 is a unit and a1, a2, an all are nilpotents in R. Then all of a1x, a2x square, anx to the power n are nilpotents, and hence their sum a1x plus a2x square plus anx to the power n is a nilpotent element in Rx. Since a0 is a unit and this sum is nilpotent, we know that sum of a unit and a nilpotent in a ring is a unit, and from which it follows that a0 plus a1x plus a2x square plus so on plus anx to the power n is a unit. For the converse, we will use principle of induction on degree f(x). If degree f(x) equal to 0, then f(x) is nothing but the constant polynomial, and we have already assumed that the constant term is unit, so f(x) becomes a unit. We make our induction hypothesis that the result holds for every non-zero polynomial of degree less than n, where n is greater than equal to 0. Let us consider a polynomial f(x) of degree greater than 1, which is unit in Rx. We are to prove that a0 is a unit and all other ai, that is a1 to an, are nilpotent. Since f(x) is a unit, then there is a polynomial b0 plus bmx to the power m such that their product becomes 1, and comparing their coefficients we have all these identities. Let us multiply an to both sides of 5, that is the equation an minus 1 bm plus an bm minus 1 equal to 0, and we get an square bm minus 1 equal to 0. Proceeding similarly, we will get an to the power m plus n b0 equal to 0. Since already we have b0 is a unit, this implies an to the power m plus 1 equal to 0. Thus, an is nilpotent, and so an x to the power n. Since f(x) is a unit and an x to the power n is a nilpotent, so the polynomial gx equal to f(x) minus an x to the power n is a unit. And since degree of gx becomes less than n, by induction hypothesis we have a0 is a unit and all other coefficients are nilpotents in R, and thus the result follows. For example, consider the ring Z6. In Z6 there is no nilpotent element because 6 is square free, and Z6 contains only 2 units 1 and 5. So, it follows that the only units in Z6 x are 1 and 5. So, absence of the nilpotent elements in Z6 implies that the units in Z6 x and Z6 are same, but the case is not same over Z8, because Z8 contains 2 nilpotent elements 2 and 4. Using 2 and 4 we can construct infinitely many units in Z8 x. For example, here I have considered 1 plus 2x plus 4x square. It is easy to see that this is a unit having multiplicative inverse 1 plus. Thus, in this module we have developed formal definition of polynomials over a commutative ring with unity, and we have shown that the set of all polynomials has a beautiful algebraic structure. It is a commutative ring with unity, but again remember that it is never a field. Also, we have characterized, we have identified those polynomials which are unit. Also, here we have given definition of degree of a non-zero polynomial. In the next modules, we will see that degree of a non-zero polynomial has an important role to get division algorithm. In the next module, we will discuss division algorithm of polynomials. In the next module, we will discuss division algorithm of polynomials.